Well, hello, my little students who missed school on Friday. Hope you had a great time on your field trip. And this is the information that you need to know to finish your foldable. So let's rock and roll. Here we go. So there's a fourth law, and his last name is a little unfortunate.
So basically what Gay-Lussac's law says is that if a pressure of a gas is affected, then it varies directly with its Kelvin temperature, because remember, we can't use Celsius, and so that stays the same, and the volume is remaining constant. So if you think about this, I'm giving you a container, and I am affecting the temperature. And so if I put fire underneath this container, and the container cannot change sizes, maybe it's a metal container, then what's going to happen to the molecules inside of that box? Well, if you think about it, those molecules are going to start to speed up, and when those molecules speed up, then they're going to start to bump into each other more, and there's going to be all these collisions. And if you remember from the other day that we said that collisions was pressure. And so when we increase the temperature, we cause more collisions, so we increase the pressure. If the fire goes out and there's no longer a fire, those molecules are going to start to slow down. And when those molecules slow down, the temperature will drop. They will have less collisions, and so the pressure will go back to normal. So this is Gay-Lussac's law. Make sure you have written on the outside of your foldable. And his graph looks just like Charles's law, so I might just draw a straight line. And you want to recall that this is a direct relationship. When the pressure goes up, the temperature goes up as well. And vice versa, when the temperature goes down, the pressure is going down. So I just might label on your graph P on one axis, T on the other. It's not important for any of the numbers. So I loved this graphic. It's kind of what I just talked about. Something that you need to know, this little metal arm that is controlling the volume of the container is called a piston. You have pistons in your car, and they are what move up and down, up and down, up and down when your engine is trying to work. And so the pistons move up and down and make your car move. And so in this instance, the pistons are stationary. They are in place. They are controlling the volume, and they are keeping it constant over here. V1 equals V2. And what they're showing you here is when they light that fire, you can see those collisions. Now in your foldable, I messed up because I changed this flap and neglected to change your boxes. You have a box that's too big, so do this. In that big box, make it the same size as the small box, and then kind of shade out the part that's left over, because we want the volume of your boxes to look like they are the same size. And so I would draw this picture somehow, maybe with 5 little molecules in there. And I would say when the temperature is low, the pressure is also low. And then I would put a little flame under your second box. And then I would show those molecules colliding. You know, those little marks are showing that they're, boom, they hit. And then maybe another pair of the molecules are colliding. And so we're showing that when the temperature goes up, the pressure goes up as well. So we're going to do an example problem. One thing I noticed when we trade and graded the homework is that you guys were cutting corners. You weren't writing the formula. And you're going to see hopefully later, especially when you start the mixed gas laws homework, that if you're not writing the formula, you're going to get really confused and you're going to put numbers in the wrong place. The first thing that the mixed gas laws homework that Nancy and Brian have for you says is that number one, it wants you to label the variable. So I'm going to demonstrate that for you. If a container that is at 5 atmospheres of pressure, so that's my P. We have to figure out if that's our P1 or our P2. So if we keep skimming, look what they're asking for at the end. They're asking for the new pressure. So that's also going to be P, but we're going to call that one P2. So if we're looking for the new pressure, then it's safe to assume that this was our P1 up at the top. So that's all I mean by labeling variables. Your math teacher might have you come over and make a list. P1 equals 5 atmospheres. P2 is equal to X. That's not necessary for me unless you feel like that's really going to help you. We make on-level do it, but you guys are in pre-AP for a reason. So I am totally cool with you labeling your sentence. And then it says the pressure increases from at a temperature of 23 degrees Celsius. Remember, can't use that. Have to add 273. So this is 296 Kelvin. And that's your original temperature. So we're going to label him T1. And then we've got 85. So the 85 degrees turns into 358 Kelvin, and that's going to be our temperature 2. So we've labeled that. So at this point, we should know I've got P and T. That's going to be Gay-Lussac's law. And so we are going to write the formula. P1 over T1 equals P2 over T2. I encourage you to put a box or something around the variable that you're trying to locate. You need to isolate him. With the fraction, I'm going to encourage you to cross multiply, make it linear. It's fast, it's quick, it's easy. Do it every time. P2, T1, your box is around your variable, equals P1, T2. Notice your temperatures are flipped, or your pressures are flipped. So make sure you're plugging the right thing into the right place. Solve for P2. We've got to isolate P2 so we get rid of T1. So that leaves us with P2 is equal to, my P1 is going to come in right here, which is my 5 atmospheres. My T2 is the 358 Kelvin. And we're going to divide by our T1, which was 296 Kelvin. We put that all into our calculator, and with proper number of sig figs, we end up with the pressure of 6 atmospheres. Now, I would encourage you also to stop at this point and take a second and say to yourself, does this make logical sense? So what happened to our temperature? Our temperature increased. So if the fire got hotter, what happened to the molecules? They started to collide more. The pressure should have gone up. And check it out. It totally did. It went from 5 to 6. So I know my answer is most likely correct. Did you hear about the man who got cooled to absolute 0? He's okay now. Get it? 0K. Ha! Hilarious. So this is not on your foldable. Do me a quick favor. Flip your foldable over to the back and write Avogadro's law on the back of your foldable. All I need you to know that it exists. It's in our TEKS for the state of Texas. They say we need to teach it to you, so we're going to show it to you, knowing that we don't use it very often in the land of chemistry. But it is there, and you will see this come back into play after spring break. We get to a topic where we talk about it and show you how it was used to derive a new equation. So all I need you to know is this. So think about this, okay? N is new. You don't know what that is. It stands for the number of moles. So what Avogadro's law is saying is if I give you a whole bunch of moles of gas, you're going to need a bigger balloon to hold all of those moles. That's it. And so if the number of moles goes up, the container needs to get larger. If I take some of the moles away, the container can get smaller. Duh, no problem. But that is Avogadro's law. He's got a direct relationship just like everybody else. Again, it's saying, oh, look, I doubled the moles. So if I doubled the moles, I need to double the size of the box that holds my moles. So that's kind of common sense. That's all you need to know about Avogadro. Chemistry joke. What do you call iron blowing in the wind? Febreze. Ha! I cracked myself up. Here is your last law on your foldable, the combined gas law. So look what we did. There are letters everywhere. P1V1 over N1T1 equals P2V2 over R2D2. Not really. It's really N2T2. But it starts sounding like Star Wars if you say it fast enough. So these are all of our initial or original conditions. These are all of our final. conditions, and they're all related. And so it's crazy to think that I can always keep something constant, because in the real world, all of these things are changing at the same time. I will let you know, though, that we don't typically use the moles. And so really, when I learned the gas law, the combined gas law, when I was in high school, I merely learned it like this. And so mine looks like this. P1V1 over T1 equals P2V2 over T2. And really and truly, I hate fractions that make me vomit in my mouth. And so I cross multiply that, and I get P1V1T2 equals P2V2T1. And that is my combined gas law. If you don't like fractions and you want to learn it as a linear equation, you do that. All you have to remember is that the temperatures are on the flipped side. They are opposite of everybody else. So here's what's kind of cool about this law. If I give you pressure and temperature, and that's all I give you, then we're to assume that the volume and the moles are constant. Well, look, there's Gay-Lussac's law. If I give you, give me a second to erase here. If I give you volume and pressure, and volume and pressure, and I say the temperature was 23. Well, if the temperature is 23 and I didn't mention that it changed, you're supposed to assume that it's constant, and you're supposed to cross it out. And so if the moles and the temperature are never mentioned, or they stay constant, they're gone. And now I have Boyle's law. And so you have all of these laws. The only one that's not included in this law is Dalton. So out of this entire foldable with 6 laws, the only 2 you really need to know is Dalton. P total is equal to P1 plus P2 plus P3. Or the combined law. P1V1 over N1T1 equals P2V2 over N2T2. And if you know both of those, you know everything you need to know. So it's kind of cool. So if we look at our example here, it says a gas is cooled from 45 to 20. We know that's going to be 293 Kelvin. That's my T2. This one's going to be 328 Kelvin. That's going to be our T1. So let's think about this logically. The temperature just got colder. Well, look what they're trying to ask about. They're asking about volume. So what happens to things when they get cold? They shrink. Charles's law of shrinkage. And so we are expecting, just based on the temperature, that this volume might shrink, but we have to keep reading. The pressure changes from 103, so there's our P1, to 101.3, kPa's on the next line. That's our P2. Now, let's think about this. The pressure decreased. If I had a balloon, and I've got pressure on the balloon, and the pressure backs off. So if the pressure goes away, what's going to happen to the size of my balloon? Well, my balloon should get bigger. So the temperature is telling the balloon to shrink. The pressure is telling the balloon to get larger. So our job with the combined gas law is to figure out who has the greater effect on the balloon, the temperature or the pressure. So what we're going to do is we are going to write our formula. Since we have already labeled, I forgot one. Right here, 16 liters. Look what it says. It settles to 16. So that's my V2. So when we're looking for the initial volume, we're looking for V1. So up on the top of your mixed gas laws homework, it says number 1, label the equation. Number 2, it says state whose law this is. Well, since I have all 3 variables and they're all changing, I would have to write on my homework combined. The third thing it says to do is to write the formula. So here we go. P1V1 over T1. P2V2 over T2. I'm leaving N out of the equation. They never mentioned it. And so then I'm going to figure out what my variable is. It's my V1. I'm going to cross multiply and end up with P1, V1 T2 equals P2 V2 T1. Got to solve that for V1. So I'm going to divide by P1 T2. P1 T2. Make sure you didn't repeat any of your variables on accident. Your P1 and T2 cancel on the left. So we are ready to plug in. So I've got 5 spaces for my 5 numbers. You don't have to draw arrows. I'm merely just showing you where I'm getting all this stuff. So my P2 is 101.3 kilopascals. My V2 is 16 liters. My T1 is 328 Kelvin. My P1, my original pressure was 101.3, and my T2 is 293 Kelvin. Now we're ready to calculate. Before we do that, check your setup, and this is how I do that. I say, what can cancel? Since they're stacked, kilopascals can cancel. Since they're stacked, the kelvins can cancel. If they ended up next to each other, that means you put something in the wrong place and they can't cancel. You would make Kelvin squared, which tells you, whoa, my setup's wrong. I need to check that out. So liters is going to go on my answer. Something else we figured out kids were doing wrong on Friday is we're multiplying. Then we're divide by 103, and just like a train track, divide again by 293. Don't hit times down here or your calculator will get confused. Even with the parentheses, it gets confused. So hit divide. I don't use the parentheses. I just use them to hold my numbers. In the calculator, I never hit a parentheses. All right? So when I do all that, I'm finished. And it's V1 is equal to 17.6 because everybody in my parentheses has 3 sig figs except the 101.3 has 4. So we go with the lower number. And then I put liters on my answer. They didn't mention who the gas was, so I don't have to put CO2 or oxygen or argon or anything like that. And that is the combined gas law. So you know enough to be dangerous. And my last little joke of the day, Avengers Unite. You've got Thorium, you've got Captain America, you've got Iron Man, and you've got Superman with his kryptonite. Notice his little calic right there. Anyway, hope you had a great time on your trip. I can't wait to hear all about it. And good luck with mixed gas laws. Don't forget your lab report is also due. Love you. Bye.